Welcome to today's presentation entitled Introduction to Digital Signal Processing. My name is Dr. Jim Beatty and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center Flight Mechanics Technical Discipline team. This presentation is part 3 of a 4-part presentation about digital signal processing and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. Today's presentation, part 3 of a 4-part series, is entitled Implementing Discrete Filters. This overview slide just shows what has been presented already in parts 1 and 2 of this 4-part presentation, what will be presented today in part 3, and what will be presented in part 4, the concluding part of this series. Part 1 was entitled Mathematical Concepts, and it just defined the concepts that are used for digital signal processing, such as Fourier transforms and convolution operation, what discrete Fourier transforms are, and the fast Fourier transform, or FFT, algorithm, which is an efficient way of computing discrete Fourier transforms. We also discussed the Shannon Sampling Theorem and data aliasing that can occur with improper sampling frequency. In part 2, which was entitled Power Spectral Density Basics, we discussed how power spectral density, or PSD, can be used to estimate spectral characteristics of waveforms. And we also included a demonstration with a waveform that was constructed with consisting of several sinusoids, a constant bias, and a random component, and then illustrated how PSD can be used to examine such a signal and identify the frequencies of the waveforms that are present within it. In today's Part 3 presentation, entitled Implementing Discrete Filters, we'll discuss converting from continuous Laplace domain filters to their discrete domain, Z-domain filter counterparts using what's referred to as Tustin's rule or the bilinear transformation. We also will discuss how continuous and discrete filters can be implemented in such as in a simulation environment where you're trying to implement either continuous filters or discrete domain filters. We'll also show how the discrete filter form can be leads to a recursive equation that can be used to implement the filter based on current and previous states of the filter itself. And coming up in the final part, Part 4, which is entitled Typical GNC Applications, we'll discuss how discrete filters are actually implemented in typical flight applications, whether it's flight hardware or signal processing of sensor data or laboratory data of one sort or another. We'll discuss normalized frequency, kind of what that means and how that's important. We've touched on that a little bit in Part 1 and Part 2 of this series, but we'll discuss a little bit more in Part 4. We'll also talk about methods that you might use to verify the transfer function magnitude and phase of a discrete filter if you've been given discrete filter coefficients. If you want to double check what someone's given you to make sure you understand what they've given you, there's a simple technique where you can compute the magnitude and phase of that discrete filter. We'll also conclude with a final example of how you might use a discrete filter to implement a low-pass notch filter. So we'll build a waveform that has frequency content at lower frequencies within the range of the notch and at the higher frequencies, and show how that low-pass notch filter can filter out those higher frequencies and the content at the location of the notch. And implementing continuous discrete filters, just a word of what filters are used for. They're typically used to condition signals. That's either to remove some unwanted content at certain frequencies or to change the stability characteristics of a control loop. The first use, where you're wanting to remove unwanted content, you can define filters to be have certain band pass, which means certain bands of frequencies that they will pass through and other bands that they will attenuate. Those are generally characterized as like low-pass filters, which basically pass through the lower frequencies and attenuate higher frequencies. You can have high-pass filters that are just the reverse of that. They pass through the higher frequencies and attenuate the lower frequencies. You can also have band-pass filters, or what some people refer to as notch filters, which will pass filters below the location of the notch or the band pass, and pass content at frequencies higher than the band pass, and then attenuate the signals in the location of the notch. You can also have a reverse notch, if you want to call it that, that amplifies signals in a certain range. So those can be used to just condition or provide whatever characteristics you want in your signal. And when used in a control system, they might be used to, as I said, they will introduce phase and gain into the system to augment the stability characteristics of the basic plant that you're operating with, to give the characteristics you want so that you get a clean response, such as a step response that has the proper characteristics, and introduce stability if the basic plant is not stable. Filters can be implemented as either continuous filters using the Laplace transforms, or discrete filters using Z-transforms and recursive equations as their method of implementation. As most modern control systems utilize digital controllers, discrete filters are commonly used in current GNC applications. But quite often you'll find that the specifications of the filters or the actual stability analyses that were done for the control loop might be done in the continuous or Laplace domain. Sometimes that's more straightforward and more familiar to the guidance and control engineers. So there's often a need to convert between the two. If you're given a filter in the continuous domain, in other words, a Laplace domain filter, G of S, and you want to implement it in a discrete filter, you have to do some conversion. And there's a very simple technique for doing that we'll discuss next. The transformation from the Laplace transform, or sometimes called the bilinear transformation, and that can be used very easily to transform between the two forms of filtering. But first, before we get to that, let's just do a little brief recap of what Laplace transforms and Z-transforms are defined as mathematically. The Laplace transform, f of s, is basically the integral from 0 to infinity of e to the minus st f of t dt. So you're basically integrating a function f of t over an infinite range of times multiplied by e to the st. And then that basically transforms that signal from a time domain into the so-called Laplace domain. And it has an inverse Laplace transform which returns back to you the time series f of t from the Laplace series f of s. And it's shown as on the right of the upper equation that f of t equals 1 over 2 pi j times the integral from gamma minus j infinity to gamma plus j infinity of e to the plus st f of s ds. Similarly, Z-transforms are defined mathematically as shown at the bottom of the slide, where transforming from a time sequence lowercase x of n to the Z-transform uppercase x of z is a summation from from minus infinity to plus infinity of x of n z to the minus n. And its inverse is shown as the contour integral on the right side of the lower equation. And that contour C denotes a counterclockwise closed path encircling the origin and entirely in the function's region of convergence, and contains all poles of the x of z. And the Z-transform can be shown as just a generalization of the discrete-time Fourier transform that we discussed in part 1 of this presentation. So given those definitions of a Laplace transform and a Z-transform, it can be shown that the Laplace operator S can be related to the Z-transform operator Z by the equation Z equals e to the st. Or you can rearrange that and solve for S and say S is 1 over t times the natural log of Z, where t in this case is the sample time of the discrete system, and log e is obviously the natural logarithm. Now, based on what we said on the previous slide, since the magnitude of z is always less than 1, in other words, it's always, the z domain is defined as a unit circle around the origin that contains all the poles of z, then the domain of z, then the magnitude of z is less than 1, such that we can write an approximation for the natural log of z as 2 times z minus 1 over z plus 1. You can find that in most mathematics books. It's just an approximate form for the natural log. That can be rearranged by just dividing top and bottom by z, and that says that log to the base e of z is 2 times 1 minus z inverse over 1 plus z inverse. So then that lends itself to what's called the bilinear transformation, or Tustin's rule, that can be used to transfer between z and s. And that's, the equation is s equals 2 over the sample time times 1 minus z inverse divided by 1 plus z inverse. And also note that that'll come in handy down the road here in a few slides. Z inverse, or z to the minus 1, is the same as e to the minus st, if you look at the definition of z at the top of the page. And you might recall from Laplace theory in mathematics that you learned when you were discussing Laplace transforms, e to the minus st is just a transport lag of one sample. So basically that represents a one sample delay of a discrete sequence that's being sampled at t seconds per sample. First of all, we'll talk about how one would implement a continuous filter before we get to how you implement a discrete filter. And that's just a summary for those who might not be familiar with it. It's a very simple technique for converting from the Laplace domain to time differential equations in the time domain that one might use, for instance, in a simulation. Well, so let's consider a Laplace domain transfer function g of s, which defines a filter with a lead frequency omega L and a lag frequency omega n. So in the block shown at the upper left of the figure, it just shows some signal in the Laplace domain x of s coming in, and it's multiplied by this transfer function g of s, and out comes the output y of s. Or if we define that lead lag filter in a form that has a what's called a DC gain of 1, or a gain at low frequency of 1, then that's implemented as s over omega L plus 1, where omega L is the lead frequency, divided by s over omega n plus 1, where omega n is the lag frequency. So to implement that filter in a time domain simulation, what you would do is first break the transfer function into two parts, as shown at the bottom of the slide, where first you implement the lag part, and we'll call the output of that lag state w. Then the w then becomes the input to the final part of that filter, which is the lead part. And so w goes into the lead part and y comes out. So that's equivalent to what's shown at the top of the slide, but we've just introduced a new state w. And we'll show how that's implemented in a time domain simulation on the following slide. So as we said, we'd find a new state or temporary state that's going to be integrated, and we'll show how to compute the values for that, or the actual differential equations that will be numerically integrated in the simulation on the current slide. So again, recall the state that was added, which is basically just the output of a lag filter on the input state. So you can write then that w over w, the output of that lag filter, over its input x, is equal to 1 over s over omega n plus 1. That can be seen readily from the information on the previous slide. Or rearranging, you could say w of s times s over omega n plus 1 equals x of s. Or s times w of s divided by the lag frequency omega n plus w of s equals x of s. So then solving for s w of s, it's equal to the lag frequency times x of s minus w sub s. Now recall the s operator in the Laplace domain is a time derivative. So then that equation at the right, the second equation just above what's denoted as equation 1, can be written in the time domain as w dot equals omega n times x minus w. Or the current time derivative of w is omega n, the lag frequency, times how far away it is from the input, x minus w. And then finally implementing the last part of that lead lag filter, the lead portion, you can write then the output of the total filter y divided by that temporary state w is s over omega L plus 1 over 1. Again, just rearranging to consolidate the output into s, you can say y of s is s times w of s divided by omega L plus w sub s. And again, recalling that the s operator is a time derivative, that expression can be rewritten in the time domain as y is w dot divided by omega L plus w. So you can see equations 1 and 2 then will fully implement that that continuous filter. So the way you would use this is you would again define this state that's going to be integrated numerically versus time, and you'll come in and first compute from equation 1 the current derivative of w as just omega n times the input x minus the current integrated value of W. Then the output of the filter, y, is just the current derivative computed from omega dot from equation 1, omega dot divided by omega L plus the current integrated value of W. That becomes the output y, which is what you're looking for. So then in this implementation, y would result in a input signal x being passed through a lead lag filter with a lead frequency of omega L and a lag frequency of omega N. Now how would we do that for a second order filter? You do basically the same process. You would write out the transfer function for y of s over x of s is equal to just g of s, the transfer function, in this case a second order lag, which has a natural frequency of omega n and a damping ratio of zeta. So then again, just rearranging that as we did on the previous slide and consolidating to obtain the highest power of s times y on the left side of the equation as a function of lower powers of s, and then again replacing with the knowledge that the s operator is just a time derivative, you can result in the equation sort of in the middle of the page there of y double dot equals omega n squared times x minus y minus 2 zeta omega n times y dot. Now again, we'll introduce a temporary state, call it w, defined such that y dot equals w, or conversely w is the time derivative of y. So then replacing that in the equation just above it that's unnumbered, you end up with equation number 2 that says w dot is omega n squared times x minus y minus 2 zeta omega n times w. So then those two equations, 1 and 2, can be used to define states that must be integrated, y dot to be integrated to come up with y, and w dot to be integrated to come up with w. So at any time as the simulation progresses, then you come in with a value of x, a current integrated value of y, and a current integrated value of w, and from equation 2 you say that then the current derivative of w dot, or the derivative of w dot, is the lag frequency squared times the current input x minus the current state y minus 2 zeta times omega n times the current state w. Then you can also then write y dot is equal to the current state, integrated state of w. So those two equations define the states y and w that need to be integrated, and that thereby those two states then will implement that second order continuous filter. Now to implement the previous, go back to the previous first order lead lag example as a discrete filter, how would we do that? And again, we will write the Laplace domain transfer function as shown earlier, that g of s is s over omega L plus 1 in the numerator and s over omega n plus 1 in the denominator, where omega L is the lead frequency, omega n is the lag frequency. Now again, with Tustin's rule, or the bilinear transformation, we can write that s is approximately equal to 2 over the sample time times 1 minus z inverse over 1 plus z inverse. So substituting that into the transfer function g of s, we can write it as g of z now. And by carrying out some arithmetic or algebra, you can then show that's equivalent to the form shown in the center of the page, or towards the bottom of the page, where g of z is a polynomial in z inverse a0 plus a1 times z to the minus 1 divided by 1 minus b1 times z to the minus 1. And that is the recursive equation for implementing that discrete filter. And we'll show how that's actually is implemented in a couple of slides here. And in this example, again, if you follow through all the algebra involved, you can show that the coefficient a0 in that numerator transfer function is equal to what's shown there in terms of the quantities such as omega L times t over 2 and omega n times t over 2. Also, the coefficient a1 in the numerator of the transfer function can be expressed as shown there, and then finally the term b1 in the denominator of the transfer function can be shown as listed there as well. So how would this be implemented now that we have that discrete transfer function g of z? So again, doing the same kind of process we did for the continuous domain filter, now we'll say we have some input x of n coming into the discrete filter g of z, and the output is y of n. So then y of n would result in that x of n having been conditioned with a lead lag filter. So substituting the expression for g of z that we obtained on the previous slide as a polynomial in z inverse in the numerator and denominator, then rearranging, we could rewrite that as y sub n times 1 minus b1 z inverse equals x sub n times a0 plus a1 z inverse. Now again, since z inverse equals e to the minus st, as we described earlier, it's basically nothing more than just a delay of one sample t. So this equation above can be rewritten in terms of the current and previous samples of the input signal x sub n and the output y sub n. So again, y sub n, solving for y sub n in the equation above, equals a0 x sub n plus z inverse times a1 x sub n plus b1 y sub n. But z inverse x sub n is nothing more than the previous value of n, previous value of x, that is x of n minus 1, and z minus 1 of y sub n is nothing more than the previous value of y, or y sub n minus 1, so that the recursive equation that would implement that discrete filter now is y sub n, the current state, equals a0 times the current value of input x sub n, plus a1 times the previous value of input x sub n minus 1, plus b1 times the previous value of the output y sub n minus 1, where now n just runs from 1 all the way up through the size of the input x sub n. And so note that this implementation of the discrete filter now does not require any integration of any states. It's just algebraic equations, which are easier to implement in digital controllers. But you still have the memory, if you want to call it that, that an integration gives you, and that is those previous states. The x sub n minus 1 and y sub n minus 1, those obviously must be saved. You have to save the previous states of those, previous values of those states, and those past values are analogous to what an integrator does. It just remembers how you got to where you are. So you haven't really done away with the integrations, you just made it easier to implement, that you're doing it now with just algebraic equations. You can also write another form for g of z that we showed on the previous slide for just a simple lead lag, and sometimes you'll see this, so I'll present it just so it won't catch you by surprise if you happen to see a discrete filter for a lead lag implemented in this form. As shown before, recall that for the magnitude of x less than 1, you can write e to the minus x as 1 minus x over 2 divided by 1 plus x over 2. So the coefficient b1 that was in the denominator of the transfer function g of z can be written, you can show it can be written, or it was defined as b1 equals 1 minus omega nt over 2 divided by 1 plus omega nt over 2. So using the approximation above, that's approximately equal to e to the minus omega nt. So then you can write that expression g of z on the previous page as a0 plus a1 z to the minus 1 over 1 minus e to the minus omega nt times z minus 1, where again t is the sample time of that filter, or the update rate of the filter. Omega n is the lag frequency. And also note that with the same approximation, you can rewrite a0 and a1 as follows. a1 was just defined 2 slides ago as 1 minus e to the minus omega nt over 1 minus e to the minus omega lt. And then a1 can be written as minus a0 times e to the minus omega lt. So then that transfer function g of z can be written in terms of exponentials as shown at the bottom of this slide. And that's very commonly done. Now, what I'll show here is a recursive equations for implementing discrete filters of any order. The examples we showed earlier was just a simple lead lag, so it only had 2 coefficients in the numerator and 1 in the denominator. And I'll show here, this is just a general form of any discrete implementation of a filter. Now I'll jump first to the footnote on this page where it says, one general form of the recursive filter is as shown at the top of the slide here. I'll make a couple of things that you need to be aware of when you're working with discrete filters. Note that equation at the top of the slide. In the denominator, all the coefficients are implied or assumed to have a negative number on them. So 1 minus b1 z to the minus 1 minus b2 times z to the minus 2 minus b3 times z to the minus 3, etc. That's not always universally done. So sometimes if a person gives you coefficients for a recursive filter, it's incumbent on you to understand how those have been defined. As I said, some people don't assume that -1, so their denominator would be 1 plus b1 z to the -1 plus b2 z to the -2, etc. And also, sometimes that leading factor of 1 is not a 1. So instead of it being 1 minus b1 z to the -1 as shown, it might be b0 minus b1 z to the -1. And it just all depends on how the person decided to define the algebraic manipulations that we showed earlier when you implemented Tustin's rule. So it needs to be very clear when you're working with someone who gives you discrete filter coefficients, how did they define the coefficients in those filters. But the form that's shown at the top of the page is a fairly common form, and I won't say it's universal, but most of the time it's shown as defined there. It's best, as I'll show later in this presentation, how you can use those discrete filters, those coefficients, and compute the magnitude and phase, or the Bode plot of that filter. And you can, it's probably best to do that whenever you receive coefficients from someone else who may not be certain how they define them, such that if you implement the discrete filter and you don't get the correct transfer functions you're looking for, one of the most obvious problems is they were not defined as, the denominator was not defined as shown in the equation up above. But given that that form at the top is how you've implemented your discrete filter, then again you could just rearrange that. If the transfer function is y over x, where y is the output and x is the input, y over x equals that g of z as shown, that can just be rearranged to get y sub n in terms of x sub n and its previous values, and y sub n and its previous values as shown before. So you get equations like recursive equations, as they're called, such as shown at the top of the slide. Y sub n equals a0 x sub n plus a1 x sub n minus 1 plus a2 x sub n minus 2, etc., plus b1 y sub n minus 1 plus b2 y sub n minus 2, etc. And note there that those n minus 1, n minus 2, n minus 3 indices just refers to previous states of the input x and the output y. So x sub n minus 1 is the previous value of x for any value n. X sub n minus 2 is the previous value of the previous value, or the second oldest. X sub n minus 3 is the third oldest, etc. And the number of states you have to keep track of is just dependent on the order of that filter, whether it's a lead lag or a second order, or maybe a couple of second orders multiplied together. And so it can get fairly large depending on the form of the filter that you're implementing. Now, what's the distinctions and maybe advantages and disadvantages of continuous filters versus discrete filters? Well, one of the advantages of recursive filters, as I mentioned earlier, alluded to earlier, they can be implemented as standalone algebraic functions. And by standalone, I mean they don't require numerical integration, and I'll call it its interface with the controlling process. If you're, say, implementing these in a computer simulation, quite often the numerical integration of various states in that simulation may or may not be easily to get to, so that you would have to have some interface with that numerical integration process to add a state that you want to have it integrate, and sometimes that's not an easy thing to do. Whereas with discrete filters, they're just algebraic equations, and it's up to you all you have to do to implement those filters is just remember the previous values of those filters from one call to the next call of the function that they're in, and they can be implemented just as those algebraic equations. The most disadvantages, I guess you would call it, of discrete filters are described as the most common causes of problems that you'll find, and there are a number of things you can do wrong with discrete filters. As mentioned earlier, probably the most common mistake, and I can't emphasize it enough, you need to understand how the denominator polynomial coefficients were defined. And so one of the most common causes of problems is you did not, the person who defined them for you, defined them differently. And so you can get really bad results by not understanding how those coefficients in the denominator were defined. The discrete filter might not have been as defined in the standard form as shown before, and one of the more common causes there is one of the following. Either the leading coefficient in the denominator was not a 1. In other words, instead of 1 minus b1 z to the minus 1, it was something like b0 minus b1. So make sure you understand how it was given, and also, as described earlier, that if the polarities in the denominator don't include that assumed value of minus 1 on them, you can have a polarity mistake in your denominator, and that'll wreak havoc on your recursive filter as well. Another extremely common problem is if you don't call that filter at the rate for which those coefficients were defined, as shown by the symbol T here, you won't get the results out of the filter you expect. So if you just call the filter, even though you have the filter coefficients defined, if you call it at a different rate than the T that was used in the calculation of those coefficients, you will get a frequency shift in the filter characteristics. So that's again a very common mistake. If you think you're calling it at 50 hertz and somebody gives you coefficients for 50 hertz and you actually call it at 20 hertz, you're going to have a problem. Another common mistake is if you forget to save the previous states for inputs, x sub n minus 1, x sub n minus 2, up to whatever the order of the filter is, or the outputs, y sub n minus 1, y sub n minus 2. If those are not properly initialized, or if they're not saved from one update to the next of the filter, you'll have some issues. And then finally, there's confusion over what's referred to as normalized frequency versus what's called real frequency, and we'll talk about that a little bit later in today's discussion, as well as in part 4 of this presentation. Now we'll do a numerical example of a discrete lead-lag filter using the information that's provided earlier. So we'll go back to the example that we showed earlier, where we illustrated Tustin's rule there. We're coming into the filter in the Laplace domain. We have some signal x sub s, and output of that lead-lag filter is y sub s. And then the lead-lag filter is defined as s over omega L plus 1, where omega L is the lead frequency. That's in the numerator. Then in the denominator, it's s over omega n plus 1, where omega n is the lag frequency. Again, both of these should be, omega L and omega n are in radians per second. So now we'll define some numerical values to the lead and lag frequency and the sample interval t. So we'll define the lead frequency to be 10 hertz, so that's 2 pi times 10 hertz in radians per second, or 62.8318 radians per second. Let's define the lag frequency as 1 hertz, so that's 6.28318 radians per second. And let's define a filter sample interval of 0.01 seconds, and that would correspond to an update rate of 100 hertz with this discrete filter. So using the equations we had shown earlier in this slide, we can compute the coefficients in the numerator of the discrete filter, A0 and A1, as shown. And then the g of z, the discrete or z-domain transfer function, can be written as shown in terms of the coefficients on z to the minus 1. So in the numerator, you have 0.130540 minus 0.069642 times z to the minus 1. And in the denominator, you have 1 minus 0.939101 times z to the minus 1. Okay, now we'll show a MATLAB or Octave commands that you could use to implement the example that we showed on the previous slide. So the first part of this slide is just that we're going to define what the constants are, the lead and lag frequencies in hertz, and then what their counterparts are in radians per second, what the sample frequency is, and what the sample interval t would be. Then just below that is, we'll, just for reference, it will be plotted in a couple of slides from now to compare with the discrete filter. We'll compute the magnitude and phase and frequency of the continuous domain transfer function as shown by that first calculation. Then we'll define the recursive filter coefficients B1 and A0 and A1. And then towards the bottom of the page, we'll define a 4096 point impulse response function. And all that means is that we're going to find a function that's 4096 elements long. It's all zeros to start with. And then we'll, after computing it to be filled with zeros, we'll set value number 1 equal to 1. That's what an impulse response function is. It has a value of 1 for the first sample and 0 for all others. Then we'll actually use a recursive filter, which is basically implementing the equations that I showed earlier for how you would condition a filter if you know what the numerator polynomial A is and the denominator coefficients B are. Then I'm going to pass that impulse response function into that filter into that recursive filter, and the output that I'll call x here is the filtered value of that impulse response, and that will basically implement the you can use that to compute the magnitude and phase of that lead lag filter. The recursive filter that you see there is not a built-in MATLAB function. Again, that's just an implementation I've constructed for doing recursive filters as described a couple of slides ago. And then how we would, once we have the value of x, which is the impulse response that's been run through that lead lag filter, we basically do a discrete Fourier transform of it using FFTs, and that's what that last function call down at the bottom of the slide here, or DFT underscore FFT. Again, that's not a built-in MATLAB function. That's a discrete Fourier transform calculation using fast Fourier transforms, and we discussed that in part 2 of this presentation of implementation details for how to compute discrete Fourier transforms. So now we'll actually show the gain and phase, or magnitude and phase of this particular transfer function. First we'll show the discrete, and on the next slide we'll show how it compares with the continuous domain transfer function. A couple of things I want to note about this discrete transfer function magnitude and phase, though, before we go to the next slide. So shown here on the top is the magnitude in dB versus normalized frequency, and on the bottom is the phase in degrees versus, again, normalized frequency. A couple things to point out here that we discussed in the previous parts of this presentation. Note that the red line only goes out to a frequency, normalized frequency of 0.5. You see the arrow on the top slide that points to, note that the last frequency is 0.5. And again, that's because the frequency range, normalized frequency range for discrete Fourier transforms is up to the Nyquist frequency, which is half the sample interval, which means that's a normalized frequency of frequency divided by the sample frequency of 0.5. So you'll note the output of that discrete Fourier transform on the previous slide of the impulse response that has been filtered by the lead lag filter only goes to 0.5. Now on the next slide we'll compare that frequency response of the discrete transfer function with the continuous transfer function that was defined in the Laplace domain. And to do that, we computed just a Bode plot of the continuous a couple slides ago. I showed you the MATLAB commands for that, and we'll actually plot those together now, with the upper plot being the magnitude versus frequency and the bottom part being the phase versus frequency. However, note now, to be able to more directly compare with continuous domain, I've converted the discrete domain frequency from normalized frequency to actual frequency. So you'll notice in both on the upper plot and the lower plot, the second semilog x command, which is plotting a semilog scale, the frequency that's shown now in red, I've actually plotted the FREQ parameter that came out of the DFT, discrete Fourier transform function, has now been multiplied by the sample frequency fs. That converts that normalized frequency, which is frequency divided by fs. If you multiply by fs, you get basically that frequency converted back to hertz instead of normalized frequency. And you'll notice the first semilog x call, I divide the frequency out of the continuous Bode function by 2 pi, because what's coming out of my version of the Bode plot is the frequency in hertz. In radians per second. So I want to divide it by 2 pi radians per cycle to convert it to cycles per second, or hertz. So you'll note very good agreement for this simple lead lag of the gain and phase for a discrete filter. And you notice as you start getting out at higher and higher frequencies, approaching the Nyquist frequency, you see the bottom curve shows a little bit of difference in the phase towards about 15 hertz or so. And that's to be expected, and we'll discuss that a little bit too, of how you can things you can do to preserve some of the frequency characteristics if the region of interest in your filter happens to be getting close to the Nyquist frequency. So this concludes part 3 of this 4-part series entitled Introduction to Digital Signal Processing. We'll do a brief recap here of what we covered so far in the first 3 parts and what we will cover in the 4th part to follow. In part 1, which is entitled Mathematical Concepts, we covered just the basic preliminaries for the mathematics that are required to perform discrete Fourier transforms, and which are the basis for digital signal processing. And we discussed Fourier transforms in general and what the convolution operator is. We also discussed what discrete Fourier transforms mean for discrete sequences of numbers, and how fast Fourier transforms, or FFTs, can be used to efficiently compute discrete Fourier transforms. We also discussed in part 1 the Shannon Sampling Theorem and data aliasing, which is related to how often or how fast you must sample signals to preserve their frequency content. In part 2, which was entitled Power Spectral Density Basics, we covered the following. We talked about what PSDs are, how you compute them, and what they're used for to estimate the spectral characteristics of waveforms, and some common built-in tools that are provided in PSD packages to allow you to condition the signals to better interpret what content they contain. And we concluded that part 2 presentation with a demonstration of a particular waveform where we built a time series waveform consisting of a number of sinusoids, a bias, and a random component, and showed how the PSD capability can be used to identify the signal characteristics of that aggregate time series. In today's discussion, part 3, which was entitled Implementing Discrete Filters, we showed how to convert from continuous Laplace domain filters into Z-domain filters using Tustin's rule of bilinear transformation. We also showed the standard form for the recursive filter, discrete filters, and how you can use those standard forms for the Z-domain transfer function and build a recursive filter that will implement a filter of any size you want. We showed examples of a first-order lead lag, and that can be extended to higher-order filters as well. In part 4 of this presentation, which is entitled Typical GNC Applications, we'll show what we mean by normalized frequency, and we talked about it a little bit today, and we talked about it a little bit earlier in the presentation, but we'll discuss that a little bit more because, again, that's a common source of confusion with people when you start trying to implement filters as we would in a GNC application. We'll also show, as I mentioned earlier, one of the common problems with using discrete filters is you really need to understand how the discrete filter has been defined, and especially if you're working with someone else, if they give you coefficients for a discrete filter, the first thing you probably ought to do is verify the transfer function magnitude and phase using techniques that I'll show in the next part of this presentation before you actually implement your filter. That will save you a lot of problems in the checkout of those filters. And then also we'll show an example of how to use a discrete filter to implement a low-pass notch filter, and we'll build a time function or series that has low frequency component, high frequency component within the region of the notch, and we'll show that once you pass this signal through this discrete filter, you will in effect remove the high frequency in the notch component, and you're left with just the low frequency portion. So I hope that you have found this presentation today to be useful and informative, and I invite you to continue with part 4 of this discussion. Thank you.